Welcome. In this video lecture, I am going to talk about the traveling salesman problem. So first of all, we will see what is a traveling salesman problem, and then we will try to build a mathematical model which is basically provided by the Miller-Tucker, which is MTZ mathematical formulation, which is the integer linear programming based formulation. And then we will solve this mathematical model using IBM ILOG OPL CPLEX Studio. So first of all, what is traveling salesman problem? So the traveling salesman problem is when a salesperson, which means the person who is traveling to all the cities once and before returning to the home. Okay, so which means if we have the five cities, it is going to from one to five and then back to one. Okay, so that is origin that is called as a traveling salesman problem, right? Like if I show it in a graphically, which means so this is one, this is two, this is three, this is four, this is five. So he need to travel all the cities once, okay, and then return back. Okay, so every city he has to visit and then return back to home. That is called as a traveling salesman problem, and the objective is that person must travel the minimum distance. So which means we need to find out such a route that he or she should travel the minimum distance. Okay, and the distance between the each city is given. Okay, which means we know those distances, and we are assuming that the person can move both the directions, right? So in order to mathematically formulate this traveling salesman problem, so first of all, we are saying that how many number of cities that person want to travel. So I am developing a set, or you can say it's an index. So n is representing the number of cities. So I is basically representing whether it is city 1 to up to n. So this is a set of cities, and then we have the parameters. So right now we are representing the distance from city I to city j is with respect to cij. Okay, so that is indicating how much distance is from city I to city j, which means from city I1 to 2 or 2 to 1. Okay, as we see mentioned earlier that the distance between 1 to 2 and 2 to 1 would be the same. Okay, and the decision variables we have in this MTZ are the two type. One is Xij, which is always a binary variable. It is indicating the value of Xij would be 0 if there is no travel between I to J. Okay, and if we are traveling from I to J, and there would be equal to 1, which means if there is a path, whereas ui is basically a dummy variable which is basically going to eliminate the subtour. So what is the meaning of the subtour? That means if I am going from 1 to 2 to 3, and then we are moving towards 1, so this is a subtour. So the condition is that the person must travel all the cities, okay, at least once, okay, and then back to over here. Okay, so all the cities once and then back to home. So there should be no a subtour among those cities, right? So we would like to eliminate that subtours. Okay, so in order to basically formulate this model, so we can take the help of the transportation problem. So as you know that in a transportation problem, the objective is to minimize the total distance. That is basically indicating the distance from I to j, and xij would be our decision variable. So this is going to be 0 if we are not traveling from city I to city j. It is going to be 1 if we are traveling from I to j, and then we multiply with the distance which the person is covering from I to j. The first constraint is basically it is indicating that each city is left exactly once. Okay, which mean when he is moving from I to j, so I is 1, so he is exactly lefting that city only once, which mean visiting or traveling that city only once. So for that we are saying j is equal to 1 to n, which mean we are going from 1 to n. All we would like to visit all the cities, but the j should not be equal to I. So here the index I and j are indicating every particular individual cities. So that's why we are saying I and j should not be equal, which means if I am in a city 1, so I cannot go to city 1. Okay, so it should be different. Okay, so we are saying the xij should be equal to 1, which is basically forcing that the person is lefting or moving from that city only once. Okay, so I to j should be equal to 1, where I is the element of n is basically the number of cities. So you can open it up. Okay, that means we are saying that if we are at city 1, okay, if I is equal to 1, so j could be 1 plus city 1, j could be 2, up to so on, up to if I is 1, j is n, and then plus if I is equal to 2, okay, and so this is equal to 1, and then if I is equal to 2, j is equal to 1, if I is equal to 2, j is equal to 2, up to so on. So we have n constraints over here. Same is the case, the person must enter only once in the jth city. So for that, that is basically I 1 to n for we are going to sum with respect to I, whereas for all the j's, and j's is the element of these cities, that j is from 1 to up to n. So these are also n constraints we have. And then we have the subtour elimination constraint, which is known as MTZ constraints. So here we have a dummy variable, which is UI. Okay, or you can also say that this UI is also indicating the route order also. Okay, so how we are going to represent this one? So I am explaining in this way that ui minus uj plus n into xij must be less than or equal to the number of cities minus 1, where I and j should not be equal. I is not equal to 1, j is not equal to 1, so which means we are starting the I is from 2 to up to n, where we are fixing ui is equal to 1, so which means we are fixing the starting city, so that is equal to 1. So let me explain in more detail this particular constraint. So we are saying that ui is basically helping us to encode the position of the city in the tour. Okay, so for example, if we in a start we are fixing that u1 is equal to 1, which means we are starting from city 1, and then we are going to visit all the other cities, which is from 2 to n. Then the tour goes from city I to city j, which means the xij is going to be 1. So which means if over here the city xij is equal going to be 1, then we can write down this constraint this way, which is ui minus uj plus n is less than or equal to n minus 1. If we simplify this constraint, we are getting ultimately this one, which is indicating that the city j is always greater than from the city I, which we are saying that I should not be equal to j. Okay, and obviously when we are saying we are moving from 1 to 2, so this constraint is going to be true. Okay, that is basically indicating the order of the constraint cities. Okay, which mean I must come before to the j, as I mentioned over here. So if xij is become 0, then this factor is going to be 0. That is, we are getting this constraint, and this restriction is also be going to be true. Okay, so which mean if this is city 1, this is going to be city 2, and the number of cities, let's say we have 5 or we have 2, so in every case this constraint would be true. Okay, so this is all. So with the help of this particular constraint, that is this one, we can eliminate this subtour elimination. So what was the subtour elimination? As I mentioned earlier, if we have these three set of five set of cities, okay, and we need to move only once. So if I am in a city 1, so I cannot go 1 to 2, 2 to 3 and then back, or I can go 1 to 2, 2 to 3 and then 3 to 4, then 4 back to 1. So basically I am not visiting every city. So the subtour elimination make sure that we should all um, all visit all the cities once with the help of these set of constraints. Okay, now let's take an example. Let's say if a salesman have to visit 5 cities, okay, and this is the distance matrix we have. So that means from city one to one, obviously these are going to be zero. So we are saying from city one to two, the distance is two. City one to three, the distance is nine, and up to so on. Okay, same is the case. One to two is two, and then two to one is also two. One to three is nine. Three to one is also 9. So as I mentioned earlier, that we are assuming that if the person is visiting, can visit travel from both the directions. Okay. Now let's implement this one. So basically, this particular model into the OPL CPLEX Studio. So first of all, we need to define the index. So the index we are mentioning, that is basically ij. Okay, so first of all, for that, I am basically representing this set, that is n is representing the total number of cities. So in our example, that is we are considering we have the 5 cities, so n is equal to 5. So we are saying int n, and we are saying 3 dots, that is indicating that we are representing this variable in the data file. So in a data file, I have mentioned n is equal to 5. Okay, and then we are saying range cities from 1 to n. So that means with the help of this keyword range, I am saying the city starting point is 1, the finishing point is equal to n, which is 5. So that means the range is always from 1 to 5. Okay, now we are representing a variable that is basically the distance, which we are having this distance matrix, that is basically this Cij. So we are saying that int the distance from cities to cities. So which means we have defined the two-dimensional array because we are going to define the matrix, and then 3 dots, and with the help of these two brackets, I would be able to define this one. Okay, so this is basically indicating the first row, which means from city 1 to all the other cities distance, from city 2 to all the other distance. Okay, that is this one, right? From city 3 to all the other 5 cities distance. So we have defined the two-dimensional array, or you can say a matrix, which is a distance matrix. Okay, then we have the two set of the Cn variables in our constraint. One is xij, basically, which is indicating if we are traveling from city 1 to city j. Ui is basically using the eliminates subtour, or you can say basically the order of the cities as well we are going to travel. Okay, so because xi is a boolean type, which means either it is having the value of 0 or 1. So we are saying dvar, that is a keyword in OPL to define the decision variable boolean x, and then cities, which is this one, which is from 1 to n. As well as we are defining ui, that is an integer type. Okay, so basically that is indicating the order of the cities. So that's why we are saying dvar int plus, okay, u into cities. Okay, so once we have defined this Cn variable, now we are going to define the objective function. So what's the objective function? That is minimizing sum with respect to I up to n, j I up to n, Cij, Xij. So that is how we are going to write down minimize some i's in cities, j's in cities, where I and j must not be equal. Okay, and distance ij multiply by xij. Okay, then we have the first constraint that each city left once. Okay, that is this one, from J1 to N for all i's. Okay, so this is I am saying for all i's, sum with respect to J where J is not equal to I, Xij must be equal to 1. Same is the case, second constraint that we should enter each city exactly once. So that is sum I to j for I to n for all j's. So that's why we are saying for all j's in cities, sum with respect to I in cities, I should not be equal to j, and sum of xij is equal to 1. Okay, and then we are writing down the subtour elimination. So first of all, we are fixing the starting city. That is, we are saying that UI is equal to 1. So that is a fixing, and then we are writing down this constraint. That is this one. So we are fixing UI is 1 is U1 is equal to 1, and then we are writing down for all I, that is starting from 2 to n, where I and j is not equal with each other. Okay, so that's why for I in cities where I should not be equal to 1, which is that is starting from 2 to n. Okay, that we are fixing this one, and then we are saying for all i's in cities, I should not be equal to 1, j should not be equal to 1. If I and j are not equal, then apply this constraint where we are saying ui minus uj plus n into xij is less than or equal to ni, which is equal to, that is basically this constraint. Okay, so once we have coded this one, we have also entered the data. Now we can drag and drop these model and data file. We can run this configuration, and we are going to get the results. Okay, so we got the results. That is, we are saying the person is going to travel total distance is 26. So with the help of this UI, we are getting the order, which is we are saying that from city 1 to city 5 he is going to travel, then 5 to 3, then 3 to 4, then 4 to 2, which you are also getting over here. That is, this is 1 and this is 5, so this is x1, 5 is equal to 1, so that means he's going to travel from 1 to 5. Then this is uh, x21 is going to be 1, so this is x 3 4 is going to be 1, then 2 4 2 is going to be 1, and then it is indicating that is 5 3 is going to be 1. So basically these are the decision variable in which is indicating. So this is row and this is column, so you are getting the order over exactly from here as well. You can get the distance from here, that the person is going to be travel from 1 to 5, then 5 to 3, then 3 to 4, then 4 to 2, which you are getting over here against those is 1. Okay, which means 1 to 5 is 1. Okay, then 2 to 1 is 1, then 3 to 4 is equal to 1. Okay, then 4 to 2 is equal to 1, then 5 to 3 is equal to 1. Okay, I hope you got the idea. So thank you so much. See you in the next video.